So for people in Twitch land, we're here at the annual Wolfram Summer School, and there's a room full of people here with lots of different interests, and this is the first day of our summer school, and one of my traditions for the past 15 years has been to do a live experiment to try and discover something interesting about something, and where I don't know what is going to happen in the live experiment, and that's what we're doing here. I'll be doing this in Wolfram language, and I am starting from a blank Wolfram notebook here. We will post this notebook in Wolfram Cloud when it's done, and let me just go ahead and save it. And this will be posted for people to play with going forward. All right, so the topic that I wanted to explore is a quite ambitious topic, and it has to do with the intersection of things like cellular automata that I've studied a lot, and deep learning that people are very enthusiastic about these days. So let's start off with kind of a brief refresher on cellular automata. I think probably everybody here in the room knows lots about these. So the idea of a cellular automaton, it's a very simple program. So this is my all-time favorite simple program. It's just a rule that says, given a row of black and white cells, based on the neighborhood of a black or white cell, what will the cell be on the next step? And based on that rule, we can go ahead and we can say, what do different cellular automata do, different cellular automata with the same kinds of rules do in when you run them, let's say just starting from a single cell initial condition. So let's go ahead and run a bunch of different cellular automata starting with a single cell initial condition. Let's run, let's say, the first 64 of those cellular automata. Okay, here's what you get. So there's a single black dot at the top, and then various different kinds of things happen. Okay, so we get some nested patterns. Rule 30, my all-time favorite, produces this very complicated pattern, and that's the world of cellular automata. Now the problem is, between any two neighboring rules here, there's quite a big distance. There's only 256 rules altogether, and so as you make sort of the change from one rule to the next, it's a big jump. Now, if we wanted to do something like what we do in neural networks, where we are incrementally learning, let's say we want a cellular automaton that has the following characteristics. And by the way, all of these elementary cellular automata have the feature, well, a lot of them, since I started studying them in the early 80s, people started using them as models of things. And it's kind of cool, actually, because I used to have this file cabinet where I could actually have a file folder for, you know, rule 1, rule 2, rule 3, et cetera, et cetera, et cetera. And different rules have different popularities. Like rule 90 has been used for lots of things. Rule 184, which I thought was a pretty boring rule, turns out to be the leading model for road traffic flow, for traffic jams these days. So, you know, things happen with these different rules. But the point is, if we wanted a rule that satisfies a particular objective, how do we incrementally find it? How do we do training in the space of rules? Now, we can do exhaustive search, and we've done that many times to find rules with particular characteristics, but is there a way of incrementally going from one rule to the next? Now, with these sufficiently simple rules, the distance between one rule and sort of the neighboring rule is quite large. So that's going to be difficult. But one of the questions, well, the thing I wanted to ask here is, can we invent kind of a way of thinking about a space of cellular automaton rules so that we can make incremental progress, and so that we can expect to use methods like backpropagation and gradient descent and so on of the type that are popular for neural networks? So I thought the way we would try and explore this is to, let's see if this works. The way we try and explore this is to look at some larger spaces of cellular automata and try and understand kind of the structure of those spaces using machine learning. So what I did here, this was really boring, but kind of interesting too. What I did here was I took those cellular automaton images and I simply said, make a feature space plot of those images. And so now what this is doing is it's taking the kind of the neural net's view of what the different categories of images are. So what it found was these ones that have a bunch of stripes here, it grouped all of those together. The ones that are mostly white, it grouped those together. The ones that are sort of filled in triangles, it grouped those together. Now, the feature extractors that are being used for these are feature extractors that have been trained on real-world images of, cats and dogs and elephants and things, right? So that's based on the view of the image that is sort of a human-like view of the image. But so the question is, can we understand something about this space of rules if we look at larger rules? Okay, so let's start looking at some slightly larger rules. So how do we do that? So let's take a cellular automaton, and let's say, so the cellular automaton that I was first looking at there just had nearest neighbors, okay? So there are 256 possible rules. There are 2 to the 2 to the 3 possible rules of that kind. If we go to next nearest neighbors, we'll have 2 to the 2 to the 5, or 2 to the 32, or 4 billion possible rules, okay? So let's try and take a look at some of those. So if I just take let's take a random rule of that kind. So let's say, I mean, this won't be very exciting, but we can just say random integer from 0 to 2 to the 32 minus 1. And that will, okay, there we go. And now I could say rule plot of cellular automaton of that rule. Let's see, I have to say that rule. And now I have to look up the documentation of cellular automaton to know what I'm doing here. Let's see. I would have to say, okay, k comma r. Okay, that comma 2 comma 2. Okay. So now this will be, okay, so that's the rule for that cellular automaton, okay? So it says for every one of these, for every block of cells, this is how to map something. So the thing we might want to do here is to say the nearest neighbor of this cellular automaton rule, in some sense of nearest neighbor, is the one where we just changed one bit in the outcome, okay? So what we might want to do is to say what are the cellular automata that we get to by changing by all the 1-bit changes, okay? So let's take a look at the one we already had here, this particular cellular automaton here. Let's take a look at that guy, and let's say we start that guy off from, let's say, a single cell initial condition. Let's have it run for 50 steps. Let's make a picture of that, and most likely, let's see what happens. Okay, so that's what that one does, okay? So now what I want to do is I want to figure out what are the 1-bit neighbors, the 1-bit change to the rule neighbors of that particular one. Okay, so this particular thing, if we take that guy there, we say integer digits of that, comma 2, comma 32 bits, right? Is that 32? Yeah, it's 32 bits. Okay, so there's the bit pattern. And so now what we're going to do is we're going to make all 1-bit changes to that bit pattern, okay? So we want to make, so let's see, we want to make a table of, what are we going to do? We're going to say map at of 1 minus hash onto, let's just put this thing in there. There may be a better way to do this. Anybody know a better way to do this? And let's say I there, and let's make a table. There may be a much better way to do this particular thing, but I goes up to 32. Okay, so this should make all of the 1-bit changes to all of those things. So now let's do for each of these, let's do from digits. So now this is going to, from digits of that, there, comma, 2, comma 32, I believe. No, just comma 2. Okay, so this is now that looks really weird and not.
There is an inbuilt breakcode.
What's that?
There's an inbuilt breakcode function, which is just the set of bit masks that multiply one thing.
There isn't. It's not built in, actually. I don't think. Is there a breakcode? No, I don't think so. I don't think it's a built-in function. So, I think what we want to do. Why did we just get that first? Hold on. Let me just fix this for a second here. Let's get rid of the from digits. Let me just see, what did I do wrong here? So that's the map at there, and that's the help. What happened here? Oh, there. Okay. All right. So now what I want to do here is take these, and I want to say from digits, of those, comma 2. I don't know what on earth happened here. Okay, that looks right. I don't know what I did wrong. Something I did, I goofed something up. Okay, so here are now a bunch of rules that are the nearest neighbors in, so let's take a look at what these look like. If I say array plot of, let's do this here. Let's take that thing there, and let's say we make array plot with, instead of that, we say hash, and map that over this line here, which was line 22, and let's take a look at what those look like. Okay, so that's kind of interesting. So what those, if we take those, what we can see, okay, this is kind of fun. So actually I'm going to make one change here because I want to make it so that this always has the same width, so as not to confuse some of these things. Okay, so here we go. So now what we've seen here is this is the result of a 1-bit change. So a lot of these guys, let's actually try the feature space plot and see whether we can see from that what's happening. So now remember, 1-bit changes, and we're now asking, okay, so what's happened here? Oh, that's not very illuminating, because what's happened here is those 1-bit changes, for whatever reason, the feature space plot has shown these as pretty uniformly distributed in space, which is kind of bad. Kind of bad for the program that I was hoping to execute, but maybe not so bad, because in a sense this may mean that even in this space of 4 billion rules, that the 1-bit changes still don't take us far away. And in fact, if we look up here, these, okay, so let's look for each of these. We could ask the question, well, let's look at what 2-bit changes do. Okay, so those are 1-bit changes, and we see the effect they have. So sometimes, like this one here, it's really making a huge effect. And in fact, we can probably see, like that last one, it's having a huge effect because it's changing the 00000 case. Okay, you know what? I'm going to try something different here. Instead of starting these with 1-bit initial conditions, I'm going to start them from random initial conditions. So let's take these and let's see how much more similar or not they are. If instead of starting them with this, let's seed them all with the same random number, and let's make them all random integer 2, comma. Let's see, how long do we want? Let's say, let's see, we want 200, I think, if it's going to be 50 steps. Well, let's just say 150. Okay, so now what this should do is generate, splat. What did I do wrong here? Let's see, I want that. Oh, no, that's very wrong. It's going to have 2's in it. I want that. Okay. Okay, so now what this is doing is it's showing us, instead of from a single cell initial condition, it's showing us from a random initial condition what the, and so here, maybe this is more robust in terms of seeing what, so let's say that we want to evolve towards something that has some particular characteristic. For example, let's say we want to evolve to something where there is some, let's say half black and half white. So let's take these rules here and let's ask the question for each of these rules. Let us say, let me see what happens if I do this. I think if I do this and I remove that, I think this is going to give me the, let's see what happens if I do this. Maybe, yeah, okay. So I think this is going to give me the last, so what I'm going to do for each of these, I'm going to say mean of flatten of this. So, and then I might say, give me a numerical value as well. And so now what this is going to do is it's going to give me what the, okay, so they're all pretty close to 0.5. This is the average blackness level of each of these things. So that might be one indicator of what's going on in these systems, will be just the average number of black cells. So one question we can ask is, okay, there's one here which got to 0.38. So there's one question that we might ask. Okay, so here's a very simple question. Given that we make 1-bit changes, what is the graph of, how does that change in the, if all we're plotting is the, if all we're looking at is the the average density, how does that change as we make 1-bit changes? So let's try instead of just making 1-bit change, let's also consider 2-bit changes, et cetera, et cetera, et cetera, and we'll have a whole tree. So in fact, what we should have is eventually something which has, let's see, we want to have, eventually it's going to be roughly, he says, something like, let's see what this is. No, that's not the right size. So let's say, I need to look at how this works. Give a binary tree. Okay, give a k-array tree with how many vertices. So let's say 50 vertices and 4 branching 4. Okay, so eventually what we should have is something where we have, at each step, we're making a 1-bit change, and then we make a 1-bit change again, and so we'll have a branching 32 time. At each level, the tree will branch 32. There'll be 32 branches coming out because we've reached a particular state. Now, some of those branches will recombine, okay? So let's actually draw that tree. So this is now a tree. Let's think how we're going to do this. I think we might want to use nest graph. Let me see whether this is right. So let's take a, let's do the following. So let's have a list. So let's have a function called 1-bit changes of a list. And so what we want to do here is we want to have something which gives a list of all 1-bit changes to that list. Okay, so who here has a great idea for how to write a really nice piece of code that does that? Because the piece of code I have up here is kind of crummy. I mean, it will certainly work. But let's do this. Okay, so so this is now going to say. Anybody got a good idea how to do this? Come on, somebody must have an idea how to do this. Well, okay, they don't. We'll do. Okay, so let's do 1-bit changes now. Why does that say 2 there? That's crazy. Did that really say 2 back up above? Well, anyway, what we want to do is we want to say the ith one of these, and then let's say table of that I goes up to length of list. Okay? So let's try 1-bit changes on the list 1101. Okay, we should get that. Is that right? Yeah, it looks reasonably convincing. So now what we want to say is make a nest graph of 1-bit changes. Let's try that particular one, and let's say we want to do that to level 3, for example. Oh, no, that's not right. Sorry. What we want to do is say 1-bit changes, and then the initial condition for that is, let's try, I wonder whether this will work. Let's see, maybe it'll have to map over the list. Hold on. Let's take a look at nest graph. Do we have to have a map in there? Anybody know? Anybody? No, it doesn't look like it. Well, okay, I'm trying to figure out whether, okay, we'll just try it, see what happens. Okay, that was unconvincing, so my guess is that there has to be a map there. And this looks like this. Okay, there we go. Okay, that wasn't very exciting. So let's see what's happening here. So let's say vertex labels goes to all. What on earth happened here? Okay. What is going on? So this is what this is supposed to be doing is nest graph is, let's take a look what nest graph is supposed to be doing. Okay, who here, let's see, is Etienne, Christopher, anybody? What's any thoughts about what, so gives the graph obtained by applying f to expr to each of these things. Oh, I know what I want to do. I know what I want to do. I want to say flatten, comma 1 here. Well, that wasn't very encouraging either. Okay, let's see what happens if I take this function and I apply it to this thing here. So what I should get is a new list of objects. Yeah, I do get a new list of objects. And if I apply that function again, I will hopefully get another list of objects. Okay, that all looks good. So now the question is, why is nestgraph misbehaving? So let's take a look again. So this is saying, so let's take an example here. This is saying at each step, I'm going to get a list of things. And, okay, so why is this going wrong? Maybe I have to do something a little bit, why is this going wrong? Let's take a look here. So, what is happening? This should be really straightforward. Let me see. Well, I have one crazy idea which will certainly work, but it's a real hack. Let us do the following. So let's say, let's put an F in there. I have a feeling this may work. So let's do this. Let's say f/@that, and then let's say, I'm wondering if nestgraph is looking at these lists and concluding that the things inside them are, so let's say that thing with f goes to identity. I mean, this is a hack, but let's see whether it will solve the problem, and then we'll go back and figure out what should have happened if it does. Well, that's even worse. Okay, let's go back up here. Oh, that's very curious. So that basically is telling us that the only graph we have is something that goes from, okay, let's see. Well, we don't absolutely need this nest graph thing, but I thought it'd be a useful way of displaying what's going on. So let's take a look at what this nest graph here is doing, just as an example. So this is taking, okay, so this at each step is taking a list of things, and at each step, for example, that thing there is going from there, and it's giving us the first level of this will be range 09, will be that. And I don't really see what's different between that and what we are doing. Well, okay, and then the next level of that will be applying this thing to that. And okay, look, I think what we can do here, again, this is a bit of a hack, but I think it will still work, is let's do, oh no, I don't want to do it that way. I was going to change this, okay, who knows how this works? No? Okay. Anybody else here? No? Okay. Well, I'm surprised that we got ensnared on this, because this is okay. We don't absolutely need it, so let's keep going and do our thing without using this. What I was going to, I just wanted to have something where we could display the result, but what we want to do is at each level, we want to make the 1-bit changes on everything. So we might start with, okay, let's start with our rule up here, wherever it was. Where was it? We started with our randomly selected rule here, this one here. And what we want to do is make the, actually this is probably going to work as well. So let's make, so 1-bit rule changes. We'll take a rule number and a width and a size, and it will do the following. It will say, take that rule, so let's say integer digits of rule number 2, n, and then let's say 1-bit changes, and then let's say 1-bit changes of that, and then let's say from digits that, 2, and so now what this is going to do is it will make, so 1-bit rule changes should take 1-bit rule changes here, should take that, comma 32, and it should give me all the rules that are one step away from that first thing. Okay? So now what I want to do, actually let's try that nest graph thing again. Actually let's see, actually what I want to do is I want to make a generalization of 1-bit rule changes where this thing is, let's make that, let's do this one for an integer. Let's clear 1-bit rule changes. Let's do this for the case of an integer, and for the case where this is a list, let's do this mapping over the list. Okay, so now let's say 1-bit rule changes just to check this works with a list there, and great, it'll make, oops, we have one mistake here. We want to say flatten that. Okay. So now we'll start from a rule and we're going to get, okay, so now let's just try our nest graph again, just in case we were confused somehow. So now let's take 1-bit rule changes, and then we want to start from this thing, and actually 1-bit rule changes of hash comma 32. We want to start from that thing, and we want to go, let's say, 3 steps. Oh, it's big, it's big, it's big. Oh yeah, this is going to be a big, oh yeah. Okay, well it worked. Let's try, okay, just for fun, let's try a much simpler one. Let's try just the, let's try something like length 8 here, and let's try, let's say, going from rule 30, for example, here, and making 1-bit changes there. So let's try that. Okay, so there's the result. So what this is showing then, and let's say here, let's say vertex labels, vertex labeling to, vertex labels to automatic. Okay, so this is now showing for the simplest cellular automata. Actually, this is kind of interesting to see. So let's try looking just at 2 steps away. Okay, we're starting from rule 30 here. And so from rule 30, by making a 1-bit change, we can get to rule 94, and we can get back to rule 30 from there by making a 1-bit change. So the minimum path to get to, for example, rule 90 appears to be going out to rule 26 and back up to rule 90 here. Okay, so this is showing us, so this is the space that we're kind of walking around on, is the space of rule numbers. And so now the question is, so for example here, let's live very dangerously, and let's look on this space, and let's try and actually make the vertex labels be little pictures of those cellular automata. Okay, so what I want to do here is I want to say this. I have to look up how vertex labels works. Okay, vertex labels with, okay, so let's take a look at, all right, so if I just take the nest graph here and I ask for, I think I can just ask for vertices, is that right? Vertex list. Okay, so that will give me a list of those vertices, and now for each of those vertices I want to make something which is that goes to array plot cellular automaton of the thing, and then let's start it off from single cell initial condition. Let's make it be 40 steps, and that's there, and okay, there we go, that slash at this thing here. Okay, so that whole thing. So this is now going to make me basically a table of pictures that I want to use. And let me just, for the hell of it, let me just make those pictures be, image size goes to, let's say, 30 pixels. Okay, so that will be small enough that we have at least some chance to see what's going on the graph. Okay, so let's go ahead and make this graph again, and then let's say vertex labels. So now let's say vertex labels, and I'm going to put everything together just so that we have it all in one place. I want to just say vertex labels, arrow, and then this whole thing here. Let's see, we want that. Oops. There we go. Let's see what this does. Okay, that's cool. That's a nice picture. Okay, so that's showing us in the space of cellular automata, that's showing us what the one-bit changes, what they do. So in fact, it's kind of disappointing because in a sense the one-bit changes, well, it's not so bad because in this world, the one-bit changes often do pretty big things. So we're going from rule 30 here to rule whatever this is here that just is a, it's doing something trivial there. Okay, so now let's look in, let's see if we can make a corresponding picture for one-bit changes in our bigger rule space, okay? So as I say, this is the, okay, so this is kind of our, this is what we want to make a geometry out of. So we're going to have a distance metric, which is the bits in the rule changing, and then we want to have it's like genotype versus phenotype. The genotype is the change in the rule, the phenotype is what the actual cellular automaton does. Okay, so let's see what we can do in terms of analyzing what the cellular automaton does. Okay, so let's try taking, let's try just making the corresponding, let's see, the nice thing about this nest graph is that it is going to not redo a bunch of vertices, because if we do the full tree, it's going to go at level 3. It's going to be 32 cubed. Is that right? 32 cubed things, whereas the corresponding nest graph is going to have fewer. So we can do that. Let's do this. Let's say, okay, we've got one-bit rule. Let's start from that rule that we had back all the way up here. Where is it? What we should do here is to actually organize, if I have my act together here, and I'd like to think I do, okay, so first of all, let's get rid of the things we're not using here, and let's get rid of that abortive nest graph, which I don't understand, and somebody should look at that and try and understand whether it's something about the design of nest graph that's kind of goofy. Okay, so here we go. Let's get rid of the things that didn't work. And let's get, okay, so that was an illustration of nest graph. That's fine. So let's say this is displaying as trees. And then let's say, okay, so here we've got, let's see, and this here could be called the simpler case of elementary CA rules. And now let's go down here, and then let's go back to our favorite rule there. Okay, so now let's go back to next nearest neighbor rules. Okay, so now we've got this thing, one-bit rule changes applied to this rule. We got 32 here, and now, oops, what did I do wrong? One-bit rule changes, that's what I want to say. Okay, there we go. So now what I want to do is for each of these, I'm going to say, I'm going to nestedly apply this, but at each step, I'm going to take the union of these things so that I don't end up with copies, with multiple copies of the same rule. Okay, so at each step here, I'm going to take that, start with this, and I'm going to say, for each one of these, I'm going to say union of that, and then this is going to give me a certain growth of, okay, so let's say 3 levels. Oh my gosh, it's already huge. Let's see, let's go length of that. Okay, so at 3 levels, we've got 32 rules at the first level. We would have 32 squared rules at the next level. Let's just make a table of, let's see how much better we're doing here. 32 to the n goes from 1 to 4 here. Okay, so we're doing a lot better for merging the ones that turn out to be the same rule. Okay, so because again, remember in this graph up here, this isn't a tree because a bunch of times when you make 2-bit changes, you'll wind up coming back to the same rule again. Okay, so let's go here and let's say, so just to divide these, just to see how pleased with ourselves we should feel, we can divide those. Okay, so we're down at 3% of the rules that we have to actually look at. Okay, so now let's ask the question for each of these. Let's just ask a really simple question for each of these rules. Okay, so let's say for each of those rules, let's just ask the density question. Okay, what the densities are for each. In other words, and then we're going to ask on this graph what paths lead us to. Let's see how to do this. So what we want to show. Okay, let's do the following. So for each of these, let's only go 2 steps out. Okay, so that's going to make a bunch of different rules. So let's say let's call this rule lists. And so that's going to make a bunch of lists of rules. So for each of those rule lists, we could go ahead and compute the average density that we get. So let's go ahead and try that. So let's say, let's call it density. Let's say density estimate. And we can give the rule number. And we can give the, actually we'll give the rule specification. So this will be a rule number, a number of, and let's say, the rule number, and the radius, and that. Okay. So now what we want to say is density estimate of that rule, and let's say a size n that we're going to use to do a size n and a t steps. Okay. So now what we want to do is we want to make a cellular automaton evolution. We say cellular automaton, and then we're going to say let's see well actually it's just that rule number kr, and now we want to say random integer of k minus 1, and then that's the width there, and then we want to say let's see, just give the result from t steps, and then we want to say flatten that, and then we want to say the mean of that, and then we want to say the mean of that, and then the numerical value of that mean, and so now that will give us, so that gives us some kind of density estimate. So for example, if I say density estimate of 30, 2, 30, 2, 1, comma, let's say I want width 400, and let's say I want 100 steps. Okay, so there's the density estimate, it's close to 0.5. Okay, so now let's go ahead and do that density estimate on all the things in my rule lists. So rule lists, so I've got rule lists, and now what I want to do is I want to map density estimate of that thing, comma, let's see, those are 2 type rules. Let's do the same thing, 400, 100. And now let's do that on rule lists, and let's map it at level 2 because we've got a list of lists, and let's see what happens. So, okay, there we go. So now these are all the densities of all of those rules. So this is the 1 level out and 2 levels out densities. So now why don't we go ahead and take those, and let's just do the very naive thing. Oh my gosh, there are lots of these. And let's just make a histogram for each of those, for each of the, okay, so what we've got here, this is pretty boring. Okay, so but actually it's not totally boring, because what we've got is there's a little tail here. Look at this, actually, this is kind of fun. So what's happening is mostly the density is around 0.5, but we have some of these rules that are going down to density actually as low as 0.3 here. So a question is, to get to density 0.3, is it just random, or was there a path that got to density 0.3? Okay, so in other words, was it the case that we made 1 bit change and then we made another bit change on top of that one, and that's how we got down to lower densities, or was it just that the densities were completely random? Okay, so how are we going to display this? So what we want to do is we want to plot, let's think, we want to show as a function, so on this, let's see, because we're trying to deal with a space where we're, let me think how to do this. We're trying to show, well, one simple thing we could try to do, let me think. We could just show this density. Okay, first step. Okay, I got an idea for the first thing to do. Okay, so here, wherever it is, what I'm going to do is I'm going to do this nest graph thing. Okay, here's my idea. I'm going to do a nest graph, and we're going to display on the nest graph. This may be a stupid idea, but we'll try it anyway. Okay, let's close up that cell so we don't have to see it all. Okay, so now what we're going to do is we're going to take these things out to level 2. So they're going to be a lot of different, and we're going to start off with that that rule that we've been using as our characteristic rule here. Okay, here we go. So that's our random rule. We're going to start with that random rule. Let me see. And we're going to change that to 32 there. And that goes to 32. Oh, actually, we don't want the vertex labels yet. We just want we just want that random rule in there. And we're just going to, first of all, we're going to generate the we're going to generate a 2-level nest graph for that rule, and which is already going to be somewhat complicated. And now the vertex list will be the set of unique rules which are gotten out to level 2. Okay, there it is. There's the unique rules. So for each of these unique rules, we are going to make a map of what the density value is. So here we're going to say density estimate of that thing. Okay, so here's my plan. Let's see, we're going to take this. Actually, yeah, okay, so this is the density estimate. We're going to say each of those. Okay, actually what we want to do is hash goes to that. Okay, so now this should, okay, so for each of those rules, we've now given a density estimate. Okay, so now what we want to do is make the graph, and on the graph we're going to use as a vertex label, we're going to use, let's say, a gray level. Let's see, we want to map this, it's between 0.3 and 0.6, so we want to make a, what's a nice way to do that? Let's use hues, for example. Okay, so let's say, instead of doing this, I'm going to say, let's use a hue there, and let's say, I think it's this. No, where's that? Where does that end? Ah, no, okay, there we go. Yeah, all right, so this, let's try this. Okay. Well, that's not so exciting because the hues don't differ so much, but let's try it anyway. So let's do this, and let's make our nest graph of the, let's see, we want to make the nest graph of the 1-bit changes there, and then what we want to say is, there are the 1-bit changes, and then let me say here, vertex labels goes to that hue list. Blah. Not so useful so far. All right, let's see what we can do with this. Wow. Okay, well actually it is sort of useful, because insofar as this is a map, insofar as this graph distance tells us, insofar as this graph is laid out so that things which are nearby in graph distance are nearby on the graph, this is not looking promising, because the blue ones are not distributed. It's like we don't have a chain of blue ones, a chain of ones that are getting darker and darker blue. We instead have something where we're pretty much, where the blue guys, let's see, that one there is, okay. All right, so let's do the following. Let's say, let's ask the following question. The ones that are the maximum hue, what were their predecessors in this graph? So for example, let's ask the question, if we look at paths that lead us to, see what I really want to do, okay, here's another idea. Okay, so the other idea is, let's make a plot of the landscape. So what we want, usually when we think about, you know, we always talk about, you know, when we're doing minimization problems, we always talk about, you know, landscapes of, so for example, let me make a landscape. So let's say we make random real. Let's try taking it to be, let's say, normal distribution of mean 0, 1, and let's say we make, let's make, actually, how should we do this? We want to, well, okay, let me just make a trivial version of this. Okay, let me make a 20 by 20 array of these, and then let's say we say list plot 3D. So this will now make a random landscape. Okay, so there's a random landscape. And if I smoothed it a bit, I could probably have I could probably make it look more like a more realistic landscape. But what we want to do is in this landscape, our goal is, if we're trying to like minimize the density, our goal is to figure out, we can have a gradient descent in this landscape, and we want to figure out which direction in the landscape do we go in order to get to the minimum value, right? But the landscape that we have is now this infinite dimensional landscape, because it's essentially a tree of, well, it's actually this graph of possible, it's a graph of possible distances. So in other words, the naive thing is we start from the original cellular automaton rule, and then we tree out all the 32-way tree at each stage. We tree out all of the levels. So, but what we want to do now is to find some way. So what we could do in a plot like this, we could say, what are all the paths down this mountain, so to speak? So for example, let's see if we can do that. Let's see how that would work just for a regular mountain, okay? So let's pick a mountain. Let's just do, rather than a minimization problem, let's actually do, just for fun, let's actually do a mountain, right? So we can get, let's say, let's do, this may be totally crazy, but let's try it anyway. Let's get, okay, so let's do, so this will now be the geo-elevation data. Okay, so that's an array of geo-elevations. Let's just turn them into numbers just so we have quantity magnitude of that. Okay, this may be totally crazy. Okay, so now if I say list plot 3D of that, then I should get a nice, let's say mesh functions arrow #3. This should now give me a nice, okay, so there's our Mount Everest. Okay, great. So now what I want to do is from the peak of Mount Everest, I want to figure out, if we look at all possible paths down it, at all possible different angles around the peak, okay, I want to actually plot those paths, and I'm going to superimpose those paths. Okay, that's the goal. So so the question now is, given an array, I'm trying to get the kind of the lines. Okay, who can think about how to do this? So I've got an array. Do you understand what I'm trying to do? So one way we could do this is maybe with image processing. We could just take out, we could extract a line. What's the best way to do it? The problem is that we have a rasterized line going around this thing. So actually, let me do a kind of a El Cheapo way to do this. So let's say, let's just set this to be, let's call that heights is line 79. And let's say we're going to do, let's say, let's call this real number analogs. And now we have the Mount Everest analog. Okay, so what I'm going to do, heights is line 79, and so now to make a naive thing, I could say just image of heights, and that will give me a, oh my gosh, why didn't that work? Oh, maybe I have to say image adjust, because it's not in the range 0 to 1. Yeah, there we go. Okay, so that's an image of the heights of Mount Everest, right? So now what we're going to do is we're going to try and slice out a line through this image. We're going to, so now one way to do that, okay, this is a really horrifying El Cheapo way to do this, would be to say image rotate. This is too shocking. Let's see, how can we get a line? There's got to be a better way to get a line. Okay, well, anyway, let's try this. Image rotate this through 30 degrees. Okay, so now one thing we're going to want to do, and now I wonder if there's an option to image rotate to have it make the bounding circle. Is Julio here by any chance? Well, I want to get it because I'm going to slice out the middle row of pixels from here. This is a real hack, okay? I'm going to slice the middle row of pixels in order to get, because if you think about a matrix, right, and I'm trying to get if I do it on the raster, I'm going to have all sorts of aliasing artifacts as I go and sweep around. And so I'm going to use the image processing stuff as a way to get rid of those aliasing artifacts. So I want to extract the line of pixels that is at a particular angle. And so,
If you want a line, you can, for example, use the polyjet components to find and then fit the line.
No, that's not what I want. I don't want to find a line in this. I mean, yes, watershed components would make, I mean, if I say, I mean, if I really wanted to be sort of exotic, I could say watershed components at %3, and then I could say, what do I do, colorize or something? Okay, so that's magnificent, but that's not what we want. It's beautiful, but it's irrelevant. Yes, image skeleton will also, but this is not what we want. We're simply trying to extract the pixels. So okay, so look, I think I can do it this way. If we do, yeah, that's a good idea. That's a good idea. Then we can, yeah, if we just make an interpolation.
Keep the XY coordinate, and you'll get corresponding Z value along the line.
Okay, so let's say list interpolation of heights. So that should give us an interpolating function. Okay, great. So now all we have to do is to take, for every around a circle, we would have a line. So let me think about this for a second. We want this is the easiest part. We just want a line through the origin at a certain angle. And we just want to say, okay, this is just trigonometry. We're just going to say, okay, so here's one way to get it. We say circle. We want the points on a line going. Okay, so here's what we want. It's r theta. So it's very simple. We want polar. What is it? Polar. What is the thing? What's the from polar coordinates? From polar coordinates, and then we say
coordinates by an angle, and then just set y to 0, and the remaining expression is the function along the x-axis. Just do a coordinate transformation by an incremental angle through the space.
yes, yeah, we could do that. That was what I was going to do with the images, but I think this is so. Okay, so here's another way to maybe do it. So we're going to have a r. Let's just check that we know what we're doing here. That's not what we're doing, so let's say from polar coordinates r theta, that will turn into xy. Okay, great. So now what we're going to do is we're going to make a, for these, we're going to say, now unfortunately this space, we need to transform this space so it goes from 0 to 1, or -1 to 1. Let's see whether we can have a way to do that. Oh yeah, great. In which they're assumed to come. So x min, y min, x max, y max. So that means that we can say x min, y min, x max, y max. Okay, so now we've got, let's say h fun is that height function. So now what should be the case, if we say h fun of, let's say 0.3, 0.4, that should, oops, that's not what we want. We want it like this, because it's expecting 2 arguments. Okay, so that's going to give a value there. Okay, great. So now what we want to do is we want to say from the polar coordinates, we want to say the value. Now what we want to do is make a table of h fun applied to the polar coordinates. We want to make a table with for each the r value. Oh gosh, how do you get? Oh, this is goofy because, well, okay, we'll at least make it in one direction. Okay, so table for r goes from, let's say 0 to 1 in steps of 0.05. And let's just do this with, theta equals 30 degrees, for example. Let's just see if it works. And so this should now give us from polar coordinates is not a valid set of polar. Oh gosh, oh that's so silly because it's a singularity in the coordinate system. Goofy. Okay, so let's do this. Okay, so now that should give us. So if I say just list line plot that should be, yeah, okay, great. So that's a profile going down from the peak of Mount Everest. Okay. So now what we should be able to do is for these, so what we're going to do is we're going to generate all the profiles going down from the peak of Mount Everest, and I'm curious what these are going to look like, and we're going to plot them all together. Okay, so now let's take, So now here, instead of this, we're going to make another table outside of that makes a table from theta from 0 to 2 pi in steps of, let's say, 2 pi, let's go in steps of 0.1. And then let's say here, let's live a little bit more dangerously here and do that. And now let's say, actually, you know what, I'm going to do these just to start off, because I did not goof this up. Let's just do this. So this is now going to make okay, so what this is now doing is this is showing the path down from the peak of Mount Everest. Why is this saying that that's not a valid set of, why is it doing that? R theta, why is it going up to 4 there? What did I do wrong? To 2 pi, that better not go from any larger than, well, anyway, okay, no matter. So let's go ahead and do these, just do more of them and see what it looks like. So let's do to 0.1, and okay, I don't know why it's doing this, but oh, those are above, oh, very stupid. Okay, the problem is that above pi, this is not going to work. Okay, so there we go. So there's the result. That was rather uninformative. That is, so for a real landscape, that is what we get for the, that's sort of what the okay, this is if we were a neural net and we were a neural net living and our loss function was Mount Everest, basically. This is saying what the paths down from the peak of Mount Everest would look like in the different ways, assuming we were just doing a straight path down from the peak of Mount Everest in each of the possible directions. Okay, that's what it would look like. So that's a bit uninformative because it's like, okay, but there seems to be some clustering here. So let's just try doing something where we just increase these a little bit since it seemed to run fairly fast. Let's try that at 0.03 or something. Okay, there we go. So this is now showing us. Now I wonder if we can get the density of these. So this is sort of showing us the bundles. We can see there are some popular bundles here of, now let's see, how can we get the density of this? Well, here's one trivial way to get the density, get it a little bit better, is to say plot style, arrow, opacity, 0.5. Is that crazy? Let's try it. Okay, so that wasn't all that informative. That at least gives us some sense of the accumulation points, so to speak, in this thing as we're kind of, in the path down Mount Everest, there's a popular way down. This rate of going down is fairly popular. Okay, so now let's look at what's the analogous thing for our cellular automaton. So what we want to know is as we go from that center one to, as we simply go a different graph distance out, how does okay, so we're going to make the analogous picture where we're going a certain graph distance out, and unfortunately we're only going to be able to get graph distance 4 or 5, although by random sampling we can get a lot further. Let's do this. Let's take a random sequence of 1-bit changes, and each sequence of 1-bit changes is going to change the density. Okay, and then and see whether we can get an analogous picture. Is Ricardo there for a reason? Oh, well, we're lucky here because I was thinking with all this number of people in this room that it was going to be absolutely boiling. So we have a different problem. And for people who are listening to this live stream, I don't mean a virtual room wherever this is a physical, never mind, that's just confusing. Okay, so let's see if we can do the corresponding thing. It's kind of cool to get this profile for Mount Everest. I'm now actually curious. Let's just try, who's got another favorite mountain? Let's do Mount Fuji, for example. Let's just see whether this picture looks about the same for Mount Fuji or not. I mean, it's kind of crazy that we can do this for real mountains, but what the hell? so let's try getting this whole flow here. Well, we could just do the same thing. All right, let's just try. I'm just curious whether it's qualitatively different. Okay, so let's do this. Anybody got another favorite mountain? Let's try Fuji. Mount Fuji. I think that's a lot more volcanic looking. Okay. Okay. But that's not going to be very interesting. That should look okay. So if all goes according to plan, the way down Mount Fuji should be pretty much the same in all directions. So let's see if that's actually true. Okay, so let's go. Let's make our interpolating function again, and then let's go ahead and show all the paths down. So this is now going to make the interpolating function. And now that's the Fuji interpolating function. And now let's go ahead and reevaluate this one here. Go down here. And, whoops. Okay. Well, that did what we expected. Okay. So that's good. All right. So let's go back to the cellular automata. And now what we want to do is from the initial cellular automaton, we're going to make a random series of 1-bit changes, and we're going to find the density path down that series of 1-bit changes. Okay, so let's do somewhere way up here. Well, actually, we can just as well write this again, and we can say random 1-bit changes. So what we want to do is for each. So we'll take the rule, and each time we'll go into the digits. We want to say into the digits of the rule.
You could use bit XOR with 2 to the power of something.
To do the change. That's a good idea. Yeah, that's a nice way to do it. Okay, that will be. Okay, so so this would be. So let's say if we want to make a 1-bit change to our rule that we keep on using for this, here we go. That's a clever idea, Vlad. Okay. Okay, so here we can say 2 to the 12, for example, ba-boom, it will have made a 1-bit change. So bit XOR, okay. Good idea. So that's the way we do this. So then what we do here is if we want to make a series of random changes, what we're going to do is each change. So to make a random sequence, we'll take the original thing here, and there we go. Let's put it up here, and then let's say this, and then let's say random. So this wants to be a random integer between 0 and 31. Is that correct? Yes, I think so. So that will be the change that we make. And then we want to say nest list of this, starting with this guy. And this will, now we'll do, let's say, 20 random changes. Okay, so this is now random rules. Each one differs from the last one by 1 bit. Okay, so we can, let's just see what these look like. If we make an array plot of the cellular automaton of this with 2, that rule, 2, 2, like this. So this will now be our random sequence of rules. Okay. So that's kind of, oh wow, oh my gosh. Well, this tells us something right here. So this is kind of interesting because what we're seeing is, this is kind of our evolution path in rule space, a random evolution path in rule space. So it's like we got these guys, and then suddenly it discovers how to stop it evolving on one side, and then it discovers how to make this kind of thing like this, and it's sort of discovering different things here. So now what we want to do is let's do our density function here. So we can do the same thing, but let's do it. Let's compute the density. Let's see, where do we have that? We had that way up here. Where was it? There we go. We say density estimate, and then we just had something like this. Okay, so now we say down here, for one of these sequences, so we can make a sequence of, so we'll make a sequence of random rules, and then we'll say make a density estimate for that sequence of random rules. We'll say apply that density estimate thing to these, and so now that will be our kind of path and density space. Okay, so let's say we go 50 steps in density in cellular automaton space, and now let's say list line plot of this, and so now this will be the analog of our, oh my gosh, this will be the analog of our path down Mount Everest. Okay, in this space, taking random moves each time rather than taking a systematic direction. Okay, so now, so let's do the same thing. Let's just make, let's say 20 of them here. Humph, he says, humph. Well, we're not seeing, so in this random, with these random choices, we're seeing, so something we could do is some kind of evolutionary algorithm where we're saying, you know, accept it only if it is a lower density. Okay, so let's try that. So let's say we, let's say what we do here, so what we're seeing here is nothing terribly interesting. We're just seeing that, we're seeing some continuity, which is interesting, I think. In other words, we're not seeing that each individual line is bouncing up and down randomly. Let's try a few more. Let's try length 80, and let's try like 100 of these. And let's also make these be opacity 0.5. No, we may be living too dangerously. Well, that's not so convincing. Well, it's sort of interesting because what we're seeing is there are patches here where it's going down, and we're not seeing, yeah, I mean, it's kind of random, but it's not like it's just jumping completely without anything. So let's now write a more of a an accept reject algorithm. So at each step, it's going to keep on trying. So let's do the following. Let's say, so at each step, so let's say move one step, and then the grand thing, and then we're going to wrap this up. But the grand thing here would be to try and use active machine learning stuff. I'm looking at Etienne here, but to try to use active learning to try and learn what to do here, to try and learn the parameters of what we're doing. But let's try this. So we're going to move one step. So we've got a rule number, and we're going to, and the goal is to move to a new rule number that has a lower density. Okay, we'll never accept a higher density. We'll just keep selecting more random points until we get a lower density. Okay, so what we want to do here is we want to say this thing here, that's going to give the new rule. So let's say, let's see, we want to basically do a while loop, I think. We want to say while, yeah, we want to do a nest while. We want to keep doing this. Is that right? We have the initial density. Okay, so we'll compute, rather lazily here, we'll compute the initial density, D0 is, actually we could have some pathology here because we're going to, unless we fix the random number generator, let's fix the random number generator so that we're not going to have a pathology where the density estimate keeps on changing from under us. Okay, so let's fix that, and now that's the density estimate for the rule that we started from, okay? So now what we want to do is we want to say while, nest while, and then we want to apply this to the rule number, and we want to say, we want to keep nesting that, and the criterion for stopping is that, hold on, what's the nest while? So repeatedly applies f until applying test to the result no longer yields true. No longer yields true. Okay, so what we want it to be the case is that the density estimate, we're going to seed the thing again, so that the density estimate here of this new rule no longer yields true. So that means that this density estimate is, let's see, is greater than d0, right? So that will mean that that will no longer yield true when the density is down from d0, correct? Okay, so let's try this. So now what this should do is it says, let's say, move one step. Actually, you know what? I'm gonna make this for right now. I'm gonna say nest while list, just because otherwise I may not be able to see what's going on. Okay, so I'll say move one step, and I'll start off with our favorite rule up here, wherever you got to. There it is. There's our favorite rule, picked completely randomly at the beginning of this experiment. Okay, so now let's say move one step. Oh, come on. Oh, we want to go. Do we want to say d0, d greater than or equal to 0? Yeah, okay, that's fine. So let's do it again. Oh, we seeded the random number generator. And so, oh, that's a real goof up. So this random integer here is no longer, okay, so there's a fix for this. We say block random of that. Is that the way this works? So block random will prevent the random number generator seeding. Yeah, okay. So we'll evaluate this with it blocked so that the random number seeding that we're doing to seed these things is not going to seep out, and because otherwise what was happening was that we had the exact same computation going on. Okay, so let's try this again. Okay, good. That's a different thing this time. Okay, great. And so that particular one, it took that long a run before it found one that was no longer, that actually led to a lower density, right? So it had to try all those rules. So if I do density estimate, if I do this thing here, what we should see is that each of those had a density estimate. Let's just try it just to make sure we know what we're doing here, of line 124. Okay, so what would happen there, so let's do a list line plot of this. So what happened is each of those had a higher density than the initial one until we got one which had a lower density. So we're all good here. So this is, oh, actually what's interesting here is that we are making, we're making a random change. Oh, I did something wrong here. What this is doing is it's making successive random changes to, rather than making a random change to the original rule again. You see what I'm saying? So if we were to do this, okay, so this is, okay, so this, if we want to do to the original rule, we can kind of hack it by just doing that. And now if we do the same thing, let's just try it one more time here. Okay, fine. That's fine. So that's making successive one-bit changes to the original rule. Okay, so that's move one step. So now what we want to do is we want to say nest list, move one step from the original rule. And so now what we should be able to do, let's say we move 20 steps here. Okay. Wow, what happened there? Oh, I made another mistake. I left it as nest while list, and I should have changed this to nest. Actually, you know what? I'm going to put this definition down again, because otherwise this notebook will be super confusing. Okay, so now let's do this here, and let's say nest while here. And now if I say move one step of this, what we should have happen, if we evaluate that, what we should have happen here is that that just comes out with one rule. Okay, so now let's try this again. Oh my gosh. Well, now, of course, what could happen, and this would be bad, is that we could be in a place in the space where you can't get out, where there's no way to get to a lower density. Okay, humph. Okay, I bet that's what happened here, right? We got trapped. Okay, so what do we do if we get trapped? So let's make a thing here in nest while. We probably want to, actually what we want to do here, let's see, why is that not letting me mouse over it? That's a bug. It's a bug. Somebody should report that. In this magnified form, it is not letting me mouse. Oh, there we go. When I had scrolled the notebook across and in magnified form, could somebody note this down? And then the thing wasn't going in the right place. Okay, at most max times. Okay, so okay, let's be really wimpy. Let's do it. Let's just say maximum of 10 times. That's really kind of wimpy because it would be nice to actually know if it was failing. Okay, so now let's try this again and let's see whether we get trapped again. Okay, so now let's go ahead and do the density estimate thing. Block random of this. Okay, so now what we should see is a progressive. Now that is weird. How could it go up again? What's that? Possibly because of the limit, yeah. Let's try. What's that?
The simple program that is in one step, if it's lower, whether it's not lower, you keep on at the same position.
Yeah, okay. Well, okay, fine. Fine. But, okay, well, so let's rewrite this then. I'm trying desperately to avoid using a while loop. Let's see. Okay, how do we do this? So we say, you know what? I wonder if there's a way to just return the, if the nest while fails, is there a way to return do you have a bright idea for how to do this?
Simply, you just go in a random direction. Density is lower. You return this new group. If not, you return the old group.
I see. Okay, fine. So we then all we do is for each one of these. No, that's not going to work properly. This is, if we want something which shows the whole, what this should do, the only bug here is that this, instead of, it's returning its best thing so far, and in the case where it hits the end point, it should return the original thing, not the, okay, so there's one way to do this, which is a real hack, which is to just, you know what, I'm gonna make a function called dens, which is my density computer here. Dens of Rn blank is this density here. So let's say, so now in this case here, it's if dens of hash is less than d0, return hash, otherwise return Rn. Okay? And if we apply that to this nest while, then even though there's a total hack and it's recomputing densities 1,000,000 times, we should be able to get this. So move one step 2 should be, let's see, let's get these two here. So what this should do is what Etienne has suggested there, which is, okay, so let's try this. Move one step 2 does this, okay. And it's got stuck, right? So now this would be the correct, okay, and we can just get rid of all that code there and just say dens, okay, great, got stuck. Okay, fine, so we're all ready to go now. So now let's say we've got these, and what we're going to do is we're going to generate a bunch of different different choices here. So let's go 40 steps here, and let's generate 100 of these things, and then let's say list line plot. So this is now going to show us in the space of cellular automata, going in random directions, always insisting on going to a lower density. This will show us what can happen. And let's see. See what happens. Maybe I okay, I'm going to eat a piece of chocolate while this thing runs. Maybe this is a mistake. Maybe it's going to run forever here. Well, let's kill that, and let's just try. Let's try 10. Okay, it's possible we're in an infinite loop here. Let's be even more modest. Let's try 20 steps, and let's just try 3. This is not hopeful. All right, let's just try running that. Okay, that worked fine. Let's try running it again. Worked fine. Try running it again. Worked fine. Okay, very hard to understand why this isn't working. Okay, so let's try table of that 3 times. Great. Let's try table of that 10 times. Well, I don't know what's happening here, so let's try list line plot of all of those. Okay. Oh my gosh, what on earth is that? Oh, that's because we didn't... Oh, horrifying mistake. What we did here was, those are the rules. What we didn't do is we didn't compute the densities. So this poor thing was trying to do a list line plot of just gazillions of okay, very stupid. Okay, so this is now, we map density across those, and let's try this again. All right, let's try the original one, see whether that goes fast enough. Otherwise, we'll ramp it down a little bit. But this should. Oops. Okay, let's actually kill this and let's try it slightly smaller one. But let's first of all let's just make sure that we know what we're talking about here. So let's just do one of those 20 steps. Ah, there's one thing we need to do here. Oh no, that's correct. That's correct. This is fine. And in fact, this one did really well. It went down to density 0.2 there. Okay, so now let's just do 40 steps and let's do 10 of them. You know what? I'm going to do something here. Let's go ahead and say, let's do n to 10 here, and let's say monitor. That is very curious. What is it doing? I would have to venture to suspect that it got stuck. That ain't moving. So something has gone wrong. So how can this get stuck? Let's look at the definition of move one step 2. Nest while. How can this get stuck? This is saying the test, it only gets done 10 times. Well, I'm mystified here. Humph. Okay, anybody have a brilliant idea what's going on? Let's just try. Well, that seemed to work that time. who knows? I mean, something is, something is wrong with, well, here we don't even need to do that. Okay, so what this is showing is for each of those, so it's showing how, as we move in rule space, it's showing how we get progressive improvement. And what's basically happening here is most of these things, they reach a certain point and then they're trapped, right? Because this is saying there is no way out by making a one-bit change. Right? We're doing a bunch of random one-bit changes, and we could even enumerate all 32 one-bit changes. We could find out, are we trapped or not? So like this green one here seems to be untrapped. So let's actually try running the same thing. Again, I have no idea why this thing got stuck. It seems it's incomprehensible to me why it got stuck. But let's try, let's just try 80, for example, there. And let's try 15 here. Let's just see whether we can make this work. Why did it stop? Well, I mean, obviously we're missing something here because something is, there's some reason why this thing is getting trapped. What a mystery.
Because every time you're trying to do somehow it's flat and then it goes down, so it has to be flat for something.
Yeah, but it doesn't know. Well, I think we're probably not going to make too much more progress here, but I think what we're, the thing to do next would be, and we can maybe go on with this at some point, the thing to do next. So what we're beginning to see is, the goal is to define a derivative, or something like a derivative, a path down the mountain in cellular automaton space. And actually, I'm somewhat optimistic, based on this last picture, that that's going to be possible. Because essentially what one said, what this basically shows us is that there is incrementality that is available. So it was not obvious. It could be the case that every time you make a change in one bit, the thing just bounces around randomly. But what this is saying, even in this 32-bit array, it's enough that making a one-bit change has sort of an incremental change, so that the thing can incrementally move from here to here to here. So that's actually pretty encouraging. And okay, so that is probably all for right now, but I think we got a few interesting things here, and probably, by doing this and by looking at these graphs and so on, we can start to map out. Actually, okay, so for me, we're seeing the derivative, so to speak, in this space of cellular automata, of how much better things got. And for me, my speculation that there is a nice way to unify kind of the world of things like cellular automata and the world of neural nets and deep learning and finding things like derivatives and steepest descent and so on, my own confidence that there is a way to do this went up a bit in this hour and a half that we just had. So that's encouraging. So now we just have to keep going on that slope and see if we can actually get a full way of doing sort of deep learning like stuff using discrete systems like cellular automata. And the goal would be to be able to discover, given a particular objective, like, for example, let's say some density thing, but that's a very simple objective, given some more complicated objective function, some complicated loss function effectively, can we incrementally learn in these ways? And I think the answer is going to be yes, and that will be pretty neat. And let's wrap up there. So, thanks.